The title for today's lecture is Project Selection. If you recall, till now we have considered the first stage of the life cycle of a project, and we have looked at phases like project identification, project appraisal, and the ultimate aim of this exercise is to select a suitable project so that you can implement that particular project and achieve your objectives. So today we are going to be talking about this important phase of project selection, knowing that we have already identified a number of projects and we have in fact appraised them. That means we have established many financial and other indicators for these projects. So we are going to look at this particular problem of project selection in a little greater detail. Now, the basic problem in project selection is that there are invariably a number of criteria involved, and in selecting a suitable project one has to take cognizance of this fact and also the fact that a project will not necessarily perform uniformly well on all the criteria. If this was so, then the selection would be a rather trivial exercise. So typical multiple criteria we have mentioned in a project could be the investment, the return, which could be measured in terms of the internal rate of return, the payback, the net present value, the risk of the project, which could be identified either in terms of the probability distribution of outcomes, or it could be measured on a subjective scale of high, low or medium risk, future growth prospects, similarity of the project to the existing business, and the environmental implications. So all these are instances of the various criteria which are relevant in a particular project and with which we have to deal with. Now, what can be done is that this evaluation of projects, in this particular process of the evaluation of projects, as I just indicated, it would rarely be true that one project emerges as the best one on all the chosen criteria. Incidentally, if this happens, then this would be known as a dominant project. A project which dominates all the other options. If it was best on the investment front, best on all the criteria, then it would be a dominant project and should clearly be chosen. So this is the definition of dominance, you can say, some extent. However, there would be a set of, in general, there would be a set of non-dominated projects, the choice out of which is not normally easy. Why is it not easy? Because you might find, for instance, that one particular project is very good on the rate of return, but is poor on the risk front. There is another project which is very good on the risk front, but doesn't necessarily guarantee a very good return. Now, how do you choose between these? These would become, there would be a kind of a dilemma, and in general, what helps you to resolve this dilemma is the management priorities. Two various criteria could help us in decision making with regard to which project to choose and which not to choose. So this is the broad framework of project evaluation with which we are going to be concerned here. Now look at the criteria in a project. We have said that there could be a variety of criteria. But one way of looking at criteria could be that we could classify criteria into either tangible criteria or intangible criteria, because we encounter both in selection of a project. Tangible criteria could be like investment measured in rupees, or it could be the return measured as a percentage. The return is 20% or 25% for a project. It could be the payback period measured in years, or it could be some annual cost measured in rupees per year. So these are all instances of tangible criteria which can all be measured, but again what we notice is that they are not necessarily in the same units. So they could either be in the same units, they could be in commensurate units, or they could be in incommensurate units. For instance, the payback period in years cannot be treated on the same lines as the internal rate of return as a percentage. You can't add them algebraically and perform all those operations which you would normally like to perform on criteria which were commensurate. On the other hand, we have intangible criteria. Intangible criteria are those criteria which are not measured, not measurable on a well-defined scale. So when you are talking of, for instance, a criterion like similarity to existing business, it would be very difficult for a firm to give a quantitative criterion or a quantitative value of how the new project would be similar to the existing business. So you might say, okay, it is poorly related to the business, or it has a high degree of similarity with the business, or you could think at best of a subjective scale. So although these are not measurable, you could at best use a subjective scale of maybe 0 to 9 or 0 to 100 as the case may be, and develop a scheme of rating these on that particular scale. So in the process, when we are choosing different projects, projects have their attributes which are either commensurate or incommensurate, or they are dealing with intangible criteria. So we have to deal with this particular problem of this is all under the gamut of what we call multi-criteria decision making. So all the principles of multi-criteria decision making would in fact come handy when one is trying to choose a particular project from this particular point. Essentially what we try to do is we try to structure the problem in the form of a decision matrix. And a decision matrix is nothing, essentially conceptually, it is a listing of the various project alternatives. So we have project 1, project 2 and so on up to project M. If we assume that we have M project alternatives which we want to compare on various criteria C1, C2, C3 and so on up to Cn. So we have n criteria on which we want to compare. Now based on the subjective scale that we were talking about, we could always convert the intangibles into some kind of a numerical score, right? So ultimately what we would do is, for each of the criteria we would have an evaluation. For instance, the first project on the first criteria would have an evaluation x11, the first project on the second criteria would have an evaluation x12, the first project on the nth criteria would have an evaluation x1n, and our objective is somehow to be able to take care of these evaluations on individual criteria and come up with a consolidated score for the project P1 and do something similar for the project P2 and so on. So if we could ultimately obtain a score for each of the projects, we would be able to rank the projects and maybe select the best one. Now this particular idea, though patently very simple, has problems because these criteria, even if they are measurable, are not in the same units. This might be payback period in years, and this might be the investment in lakhs of rupees, and this might be a percentage, this might be something else. So really speaking, even if you have these evaluations, you cannot maybe add these evaluations directly to obtain a kind of a score. So what is really being done is that you have to undergo a process of normalization to make sure that these scores on individual criteria are comparable. and there could be various methods of normalization. We would, in the course of this particular lecture, look at two procedures which are particularly useful to identify the means adopted for normalization and subsequently obtaining a score for ranking. Before, however, we go into this procedure of the decision matrix, we alluded to the concept of dominance earlier, saying that if a project was better on all the fronts, it was a dominant project, and so on. Now, I have tried to illustrate here through an example with two benefit criteria. Let us look at a comparison of these 8 projects which are shown with regard to the net present value and the return. Obviously, both these criteria are benefit criteria, that is, we want to maximize them. We want to maximize the NPV and we want to maximize the return. Now, if you just look at the performance of these 8 projects, you find that they can be plotted as points on this 2-dimensional graph as shown here. Now, out of these, you can clearly see that the project P1, for instance, the project P1 is clearly better than all P1 would be better than all projects which are lying in this particular quadrant, isn't it? That means, really speaking, that the project P1 is better than the project P2. Why? Because it has a higher NPV and it has a higher return. So it beats P2 on both the fronts, and therefore, as far as this particular quadrant is concerned, the point P1 is set to dominate all the points which lie in this particular quadrant. Similarly, if you look at the point P6, the point P6, you can see clearly dominates all points except P7 and P8, because all these points, that is project P2, project P3, project P4 and P5, are clearly inferior to the project P6. And similarly, let's look at P8. P8 we find is better. That means P8 dominates over P3, P4, P5 and P7, and yet it does not dominate over P2, P1 and P6. So if you do this exercise, we clearly find that P1, P6 and P8 emerge as the only 3 points or the only 3 projects which are not dominated by any other point. Okay? So P1, P6 and P8 therefore are known as the non-dominated solutions, which means that if we were to make a selection out of these 8 projects, we could clearly say that P1, P6 and P8 are the non-dominated solutions, because they dominate, and all the other projects are dominated by at least one of them. So it would be logical for us to conclude that if we were to select a project, we should confine our search to the non-dominated solutions, which is also known as the Pareto optimal solution in this particular situation. So the choice would then narrow down to the non-dominated solutions. But if you were to choose between P1 and P6, can you make a clear distinction? You cannot, because after all, what is happening? Look at P1. P1 is highest as far as the return is concerned and is the least as far as the NPV is concerned out of the 3 projects which are there. Now if we go to P6, what we are basically doing is we are sacrificing some return and gaining in terms of NPV. So really speaking, the choice between P1 and P6 would be governed by how much value you as a decision maker attach to the 2 criteria that you are talking about, namely return and value. and therefore this choice would have to be made based on your priorities, based on the weightages that you assign to the various criteria. So the notion of dominance, nevertheless, is a very useful one, because it gives us an opportunity to reduce the number of solutions and then confine our search only to the non-dominated solutions. But even searching the non-dominated solutions in a real life situation could be a very tough job.
Sir,
yes?
Here we are talking only about two criteria.
Yeah.
But we could have multi-criteria, like on
Precisely.
a multi-dimensional perspective. How do we look at it?
That's why, if you, very true, you can have a multi-dimensional perspective. If you have 3 criteria, you could talk of 3-dimensional space. If you have n criteria, you talk about an n-dimensional space. And that is what I said, that trying to identify the non-dominated solutions in multi-dimensional spaces would be much more difficult. But yes, conceptually, you're very right. So what is the preferred solution? The preferred solution is the solution that you ultimately choose. We call it the preferred solution. So the preferred solution could be one out of the non-dominated solution set that you have identified. It's basically the solution that you have identified ultimately. So the preferred solution could be the dominant solution if one exists. It could be the Pareto optimal or the non-dominated solution set if it exists out of these. Or it could be the selection from out of the non-dominated solutions, which will involve trade-offs and will be governed by priorities or weightages to different criteria. Like in the example that I just considered, when we considered those 3 non-dominated points, the choice out of them will have to be made by trade-offs and priorities between various criteria. So we can look at this particular procedure in little more detail. The crux to the problem really is that some kind of weightages to criteria have to be identified. So these priorities or weights to different criteria can be obtained by different ways. How? One common way of obtaining these weights is mutual consultations or opinion polls. You can talk to various management personnel and try to identify what their feeling about various criteria is, and then try to establish the weights for the various criteria. You could do it through a pairwise comparison between criteria. That means it's much easier, for instance, when you ask an individual to compare an answer between 2 criteria at a time. Say, do you consider criteria A more important or B more important? So he can say, okay, I consider A more important, and the difference is, say, medium. Then you can assign 2 criteria A, maybe 2 points, and in this manner, if there are n criteria, you would have NC2 pairwise comparisons, and you could then use these comparisons and from there determine the total votes given to every criterion and determine a possible ranking. Or you could establish a hierarchy of priorities and use the framework of AHP, the analytic hierarchy process developed by Sati. And the advantage here is that you have a well-defined computer package known as expert choice, which can be made use of, and you can develop the weightages to be given to the various criteria through a hierarchy in that particular process. Anyway, there could be other methods also, but this summarizes, you can say, the manner in which weightages to criteria could be given. Let us look at what would be the framework for a problem something like this. Say, for instance, if we take a project selection problem, our typical criteria might be, let's say, 6 criteria, just as an instance. It could be, the first criterion could be investment, and the investment could be in lakhs of rupees, and for the worst criteria it could be 10 lakhs, and for the best criteria it could be 2 lakhs. right? So there would be a range for, because we are always talking about selection from out of a set of finite number of projects. Similarly, the internal rate of return for the project set that we are trying to choose, the worst possibility could be 10% and the best could be 40%. The payback in years, the worst could be 10 years and the best could be 2 years in that sense. The risk could be measured on a subjective scale. It could be very high, which is the worst possibility, high, medium, low and very low, which is the best possibility. Similarly, the future growth could be very poor, poor, medium, good, very good. And so we could have a subjective scale like this for future growth. Similarly, similarity to existing business could also be quantified on the form of a scale like this: very poor, poor, medium, good and very good. So what we are trying to say is that each of these criteria would go from a certain worst to a certain best, and I've just given you instances of how they would go, and this would help us in the construction of the appropriate scales. Based on this information, what we might do is, for instance, if we have 5 projects and we compile the information on the 6 criteria which we just mentioned, that is investment, the rate of return, the payback, the risk, the future growth and the similarity to existing business, our starting data or the starting decision matrix would look something like this. And just to give you an idea, I have highlighted here the fact that this is the best option in bold, and the underlined one is the worst option on this criterion. Okay, so we could do a similar exercise for each of the criteria as it has been done. For instance, on the first criterion of investment, project P5 is the best because it requires only 2 lakhs as cost investment, and project P1 requires an investment of 10 lakhs of rupees. So it's the worst, underline. Similarly here, similarly for all these. Now if you then scan this matrix, you find typically if all the bolds were in the same row, you would have a dominant project. But here we don't have that kind of a situation, because you typically, what we find for instance is that project P1 is best on these 2 criteria, C2 and C6, and is the worst on criterion C1. Project P2 is the best on criteria C4, that's about all, it's not worst, it's in intermediate on other criteria, and so on. So this would be the kind of typical scenario that you would encounter when you are to choose between different projects. You would not have a clear dominant project, and therefore you are now required to choose between various projects based on this kind of a situation. Now in order to formalize these concepts, we'll take an example which we'll try to work out. This is an example that is given by Huang and Yoon, and I am trying to use this example to illustrate 2 procedures which are very commonly used in project selection. So the example is one of fighter aircraft selection, and the 6 criteria that are considered relevant for this example are the maximum speed, which is measured by a Mach number of the aircraft. The second criterion is the ferry range that the aircraft can carry without refueling in nautical miles. The third criterion is the maximum payload in pounds. The fourth criterion is the acquisition cost in millions of dollars. The fifth criterion is the reliability, which is measured on a scale from high to low. And sixth criterion is the maneuverability, Maneuverability is a very important aspect of a fighter aircraft, because you would like that the aircraft should not be too bulky and should be easy to manipulate. If you recall, during the war that we had with the Pakistanis, when was that last? Yeah, in that war, one of the advantages that the NAT aircraft had was that it was very maneuverable as compared to the other aircraft, which the Pakistanis, for instance, had the which was the aircraft that they had? Sabre jets. So that's the aspect of maneuverability. So taking these considerations, we are interested in which project, where do we buy our aircraft from? That's the project. And let us suppose that there are 4 different suppliers, alternatives. Alternative 1, alternative 2, alternative 3 and alternative 4. And the 4 aircraft that we are considering buying have these values for the various criteria. For instance, you can find that alternative 2 is the one which can run the fastest. It has a Mach number of 2.5, and it also has the highest ferry range. It can go up to 2,700 nautical miles without actually refueling. However, the maximum payload that it can carry is smaller. It can carry only 18,000 pounds, whereas other aircraft can go up to 21,000 pounds, and so on. And the criteria number 5 and 6, that is X5 and X6, which are reliability and maneuverability, are evaluated on a subjective scale, which average, low, high, average, depending upon these things. So this is the sort of decision matrix for the aircraft example. Notice in this particular case, X4 is a cost criterion and others are benefit criteria. This is the only one which we want to minimize, that's a cost. The maximum speed, the ferry range, the maximum payload, the reliability and the maneuverability are all things which you would like to maximize. So they are benefit criteria. Now, what is done is, the first step is to be able to convert the subjective factors by using a common scale. So a common scale like this from 0 to 10 is devised for cost attributes. If it is very high, we give 1 mark. If it is high, we give 3 marks. If it is average, we give 5 marks. If it is low, we give 7 marks. If it is very low, we give 9 marks. And similarly, notice that the benefit criteria would be very low, low, average, high and very high. So the benefit is increasing this way, and because when the cost is reducing, then it gets more points. So there is a difference between the cost attributes and the benefit attributes. So using this scale for intangibles, it is possible to convert that entire initial decision matrix into a matrix of numbers totally. And this is what happens. We have been able to convert the information for all these 4 projects, 4 alternative projects, 4 alternative aircraft to a set of numbers like this. And incidentally, I would now illustrate to you the steps of the procedure that is adopted in a program known as TOPSIS, Technique for Order Preference Using Similarity to Ideal Solution. That is TOPSIS. So this is the beginning step in TOPSIS. You obtain a matrix which is first of all in numerals, but these are all, mind you, incommensurate units. They are not in the same units. So we have to normalize this, and normalization would have to be carried out by using some appropriate scheme of normalization. So what is done is that in order to obtain the normalized decision matrix, we use this relationship. We say we obtain from the original decision matrix, we obtain the normalized decision matrix R using the relationship that Rij is equal to xij divided by the square root of sum of I is equal to 1 to m of xij square. Now, what is the intuitive logic of this particular number? What you are trying to do really is, let me go back to the decision matrix here. All these numbers are costs in lakhs, they are Mach numbers, right? So what is really being done is that if I square of this and square of this and square of this and square of this, and I take the square root of the sum of the squares, and then I divide all these numbers by that particular value, I would have a non-dimensional number in each of this place. That is precisely what's being done. So this square plus this square plus this square plus this square, take the square root of that and then divide each one by that number. So you will make sure that you would have a number between 0 and 1, which will be a dimensionless number here. So this is the scheme of normalization which is adopted in Topsis. So using those values, we find that we would get numbers. Each column is normalized in the same manner. So you get these numbers, and these numbers, as you can see, will all fractions between 0 and 1, the way we have normalized them. So this is the result. This is called the normalized decision matrix. Then what we do is we take into consideration the fact that these individual criteria have certain weights. So step 3 is obtain the weighted decision matrix V. We had obtained the original normalized decision matrix R earlier. We now obtain the weighted decision matrix V by multiplying each column of R by the corresponding weight. So suppose in this particular example, the weightage given to the first criterion is 20%, 10% to the second one, 10%, 10%, 20% and 30%, right? And as I indicated to you earlier, these weights may be obtained by a subjective opinion poll or pairwise comparisons or AHP or whatever. So once you obtain these weights, the earlier columns you had obtained, each column you will multiply with the corresponding value of the weight. So the first column multiplied with 0.2, the second column multiplied with 0.1, third column multiplied with this, fourth column multiplied with this, the fifth column multiplied with 0.2 becomes the weighted decision matrix, and this is the result. So the weighted decision matrix now embodies the preferences of the decision maker on the various criteria also. So you have these values. Now if you look at this particular matrix, which is the weighted decision matrix, for instance, if I identify the largest value here, this is the most desirable, so this is shown in bold, and the least value is this one, which is underlined. So the best and the worst, the best and the worst, the best and the worst. This is the other way around. This is the best and this is the worst. Why? Because this is a cost criterion. Remember that X4 was a cost criterion, all others were benefit criterion. So the least value here is the most desirable. Okay, so this is the reason why the least value in column 4 is shown as the best one, because this is a cost criterion. So this is the best and this is the worst, and of course this is the highest, so this is the best, this is the worst, this is the best, and there are two worsts which are at the same value in this particular situation. So we can then identify out of the weighted decision matrix the best and the worst options which exist out of the existing options. We have only 4 options, so out of that we can determine this particular. Now actually Topsis is unique in the sense that it looks at what could have been the best and what could have been the worst, and once it looks at these two scenarios, what is the best possible under the circumstances, what is the worst possible under the circumstances, and in fact it tries to measure it tries to rate each solution as the kind of difference or the how far it is from a utopia. A utopia would be the one which is the best possible. That's the unique feature of TOPSIS. So how it is done is, in step 4 we identify the ideal and the negative ideal solutions. The ideal solution, which is denoted by A star, and the negative ideal solution, which is denoted by A minus. These solutions are identified from the weighted decision matrix V, which we just obtained. If you can see, nothing but A star is nothing but the best possibilities. You see, for instance, all the bold figures which we had seen in the previous table, these are the, look at the previous table, these are the bold figures. They were the best possible solutions under each case, right? So we identify this, and the row that identifies the best is called the ideal solution, and the row which identifies the worst possible solutions is called the negative ideal solution. Alright, so when you look at it, you have the ideal solution this way and the negative ideal solution this way. So what is now being done is, the solution would be identified on the basis of its distance from the various solutions. Now how it is done? Step 5 is we compute the separation measures from the ideal and the negative ideal solutions for all the alternatives I is equal to 1 to n. That means you are talking of, for each, we have 4 alternatives in this case. That means there are 4 suppliers who are giving us the aircraft in this case, 4 projects. So we calculate the separation measure from the ideal as well as the negative ideal solution for all the alternatives, and how it is being done is SI star is nothing but the square root of, again, sum of squares for j is equal to 1 to n of Vij minus Vj star, sum of squares of this, and similarly Si minus is nothing but, instead of the star we have the Vj minus here. The square root is sum of squares for j is equal to 1 to n of Vij minus Vj minus whole square. And that's the kind of difference that is there for both the separation measures. Now these separation measures are computed, and for this particular example, the separation measures that we get from the ideal solution are S1 star, S2 star, S3 star, S4 star. These are the particular values, and similarly the separation measures from the negative ideal solution are S1 minus, which is computed as this value, S2 minus, which is computed as this value, S3 minus, which is computed as this value, and S4 minus, which is computed as this particular value. So the separation measures are computed for all the alternatives which you are trying to consider for this particular case. The next thing is, having computed these separation measures, step 6 says we are trying to actually determine the relative closeness to the ideal solution. So the idea is very simple. I think it's explained, it's understood by this diagram. If the ideal solution is a point here, now the ideal solution is one which is like the best of everything, the best of the Mach number, the best of everything is whatever is available if it is here. And mind you, such a solution may not exist, it does not exist here, because you don't have all the favorable features together in the same project. And similarly, all the negative features would be a point here which is called the negative ideal solution here. Your actual solutions, that is a particular alternative, is a point here. And what we are measuring is a separation. So Si star is the separation of the alternative from the ideal solution, and Si minus is the separation of the alternative from the negative ideal solution. We have measured these distances. So we then define a figure here called closeness. This is the closeness of the ith alternative to the ideal solution, which is Si minus divided by Si star plus Si minus. I hope you are convinced that this in fact would represent a degree of closeness. How? You can see clearly that if, for instance, this alternative were coincident with the ideal solution, then Si star would be 0. And when Si star is 0, this value would be equal to 1. Closeness is 100%. Right? On the other hand, if this alternative was coincident with the negative ideal solution, in that case what would happen? The Si minus would be 0, and therefore this closeness would be 0. So the closeness for each alternative, the relative closeness, is a number between 0 and 1, and the value of that number, the closer it is to 1, shows that you are closer to the ideal solution, 100% close to the ideal solution or not close to the ideal solution, right? So this is the criterion which is basically used in TOPSIS to identify exactly how you would determine the best solution.
So closeness to the negative ideal solution, is it analog to our margin of safety which we take? It's a kind of margin of safety we are considering?
No, it's not a margin of safety. It's like trying to measure that this is how close we are to the good thing and how far away we are from the bad thing. So it's not a margin of safety really. It's like trying to say that this is the worst thing that could have happened to us and this is the best thing that could possibly have happened to us. So just to measure how close we are to the best and how far away we are from the worst. So you are trying to use that concept, intuitive concept, and you have mathematically defined this terminology. The relative closeness ratings for the example that we are just talking about work out to, for instance, for the first project it works out to 0.643. For the second one it is 0.268. For the third one it is 0.613, and for the fourth one it is 0.312. And notice that the closeness rating is a number between 0 and 1, with 0 being the worst possible and 1 the best possible solution. So this can clearly identify that the first project is about 64.3%. It meets our aspirations to about 64.3%. And the second one, the third project comes next, quite close, 61.3%. And then of course it is the fourth project and finally the second project. So we can, by using this procedure, determine a ranking, and the ranking can be actually immediately, that is the what we had actually wanted to achieve. We are trying to basically rank the project and we are ranking the preference order. And the step 7 is determine the preference order by arranging the alternatives in the descending order of Ci star. And thus the ranks for the alternatives in the fighter aircraft selection problem using TOPSIS emerge as A1, A3, A4, A2. So this tells us that for the given weightages which we had, this was our problem. Our problem was able to, how do we select a project given the various appraisal criteria. So we have a mechanism using TOPSIS for selecting the projects. Now we can talk about another procedure. Let's talk about this another procedure which is you can say a competitor to TOPSIS, a simple additive weighting procedure, SAW, SAW procedure. This procedure also requires same information. So step 1 is again to obtain the decision matrix after converting the intangibles into numbers, as we had done before. So we have the 4 options, and the same decision matrix after using the information can be utilized here. Then we do the normalization. Normalization in SAW procedure is different. It says obtain the normalized decision matrix R using this particular relationship, xij divided by xj star if the jth criterion is a benefit criterion, and this is equal to xj minus divided by xij if the jth criterion is a cost criterion. Now patently this is actually very, very simple. To look at the decision matrix once again, see what we are saying is we are trying to maximize this. Obviously this is the best. So what I can do is I can divide everything by 2.5. I can divide everything by 2.5. So I would get a number. This is a cost criterion. The least cost is this one. So here, instead of dividing by this number, what I can do is I can simply say 4.5 by 5.5, 4.5 by 6.5, 4.5 by 4.5, 4.5 by 5.5. So that means I can take the reciprocals of all these numbers and sort of divide, I mean in that case multiply by 4.5. So this is what the formula essentially is. We can as a consequence of the normalization we can proceed like this. Subsequently we can obtain the final scores through these 2 steps. In step 3, using the weights for the different criteria, we obtain the weighted score for each alternative using the normalized decision matrix. This we did even in TOPSIS, but the difference now is that we are using a different normalization scheme. And not only that, we are also using a different method of scoring. That's the primary thing. Step 4 says based on the final scores. So these scores are very much like the marks that a set of students would get in different courses, and you simply have given different weightages to these courses. You take the aggregate marks, and something similar is being done here. So based on the final scores we can rank the alternatives for a decision by the decision maker.
So here the final score is get by addition of all the score of the alternative in each criterion.
That's right. The weighted score. It will be clear from this example. That's how it is obtained. For instance, after normalization you got these numbers. You remember wherever the 1 is, that shows the best possibility, and rest is less, right? 0.8, 1, this. So in each column there is a 1. In each column there is a 1. In each column there is a 1, because that is the best option. Then what is being done is that these are the weights. 20% weightage to the first criterion, 10% to the second, and so on. We multiply these weights with this and take the score. That means 0.2 into 0.8 plus 0.1 into 0.56 plus 0.1 into 0.95 plus and so on. So that's how the score is obtained. So you can say that these are like the performances of these different candidate projects on different criteria, and depending upon the weightages given to the criteria, this is the overall grade point average, the cumulative grade point average in the same sense. So based on this final score we can determine a ranking of alternatives with SAW, and this ranking shows that the rank is A3, A1, A4, A2. Now you notice that the ranking obtained by different methods need not be the same. In this case, let's compare the two. So SAW and TOPSIS, which we have considered, if we compare them, we find that SAW gave a ranking of A3, A1, A4 and A2, whereas TOPSIS gave a ranking of A1, A3, A4. So it's essentially the same, except that A1 and A3 have been reversed here in TOPSIS. The reason for this is obvious, because we have they vary in their normalization pattern and also in the pattern of their scoring, isn't it? If you give in TOPSIS we had picked up the best solution on the basis of the similarity to the ideal solution. In this we had taken a weighted average of the scores which had been obtained. So both these things are responsible for different kinds of scores that can be obtained for these particular situations. Now if we consider what we have tried to do in this particular lecture, let's look at what we have tried to achieve in this particular lecture. We have seen that project selection involves consideration of multiple, often conflicting criteria among alternatives. That is why the problem is so complicated. It's not a simple problem. And mind you, although there could be easier methods of resolving this problem, I mean, I mentioned to you right in the beginning that when we talked about dominant sets or non-dominated solutions, you could look for non-dominated solutions, but you could have a cutoff point for the performance on each criterion and then use one particular criterion to make a selection. For instance, the typical government procedure of inviting quotations and then choosing the project with the least quotation shows that you have constructed a feasible set in which the performance on various criterion of all the suppliers is known, and ultimately you are using only one criterion to rank the projects. That is again one way of solving this particular problem. But we have seen that project appraisal typically leads to evaluations which may be tangible, incommensurate or intangible. And we have seen that intangibles are evaluated on a numerical subjective scale typically to get rid of this problem. And we have also seen that a decision matrix with numerical evaluations is the starting point for multi-attribute decision making methods, and typically different methods can vary in their normalization schemes and in the manner in which the scoring of alternatives is done. So this is important to understand. These are the two major things which characterize a particular method, and the fighter aircraft example was illustrated by using both TOPSIS and SAW. So we therefore have seen that this is the manner in which a rational selection of projects after a serious appraisal could be done. And this brings us to the end of the first phase of the project, namely this is how a project is ultimately chosen and it takes birth. We will subsequently now be talking about the planning and scheduling of projects once the project has taken birth. Thank you.